Hello everyone, and welcome to this beginner course on machine learning. My name is Ethan Parker. In our last lecture, we talked a lot about data. Why was it important? What kinds of data are there? Where does it come from and what does it look like? Today we'll explore a critical yet often overlooked step in the machine learning pipeline. This is data preprocessing. Pre as in before our machine learning application uses it. Effective pre-processing can significantly impact the performance of our machine learning models. In this lecture, we will cover three key areas. These are data cleaning, which includes handling missing values and outliers, data normalization and scaling, and data encoding techniques such as one-hot encoding and label encoding. Note of warning. So far, the teaching has been like, yeah, I get this, makes sense. Now we are going to be introducing ideas and terms that are more complicated, like, dude, you said what? Kind of stuff. Watch, rewatch, and whatever to get it down. We are starting to get into the meat and potatoes here, so let's get started. First, let's talk about data cleaning. This step involves preparing the raw data by removing or correcting errors to create a clean data set. The data might have missing values. Missing values in data sets are common, and they can occur for various reasons. For instance, data entry errors, system failures, or during data collection processes. Handling missing values is essential because they can lead to biased analysis or inaccurate models. There are different ways to handle missing values. We should look at these. How about removing missing values? The simplest method is to remove records with missing values. However, this should be done cautiously as it can lead to a loss of valuable data, especially if the dataset is small. Or what about imputation techniques? Instead of discarding data, we can fill in the missing values using imputation techniques. Like mean or median imputation by replace missing values with the mean or median of that feature. Or maybe mode imputation for categorical variables. This means we use the most frequent, the mode value, to fill in missing entries. We also have predictive imputation. In cases where relationships exist within the data, utilizing predictive modeling can provide a more accurate estimate of missing values. These are all ways to handle missing data. Next, let's talk about handling outliers. Outliers are data points that differ significantly from other observations. Crazy data. Wild and freaky data that makes you wonder what in the bejesus happened here. They can arise due to variability in the measurement or may indicate variability in the data that we want to investigate. First, we have identification. Techniques like visualization, that is, box plots and scatter plots, and also statistical tests like z-score, IQR methods. These are ways to identify outliers. By the way, a z-score is a statistical measure that quantifies the distance between a data point and the mean of a dataset. It's expressed in terms of standard deviations. And IRQ methods refers to the different ways a computer system can handle interrupt requests, IRQs, which are signals sent by hardware devices to the CPU to temporarily interrupt its current operation and request immediate attention. So now that we have identified outliers, we need treatment. We could remove outliers. If justified, outliers may be removed if they are due to measurement errors or irrelevant anomalies. We could use transformation methods like logarithmic or square root to reduce the effect of outliers on the model. And finally, we have capping. We can set a threshold above which extreme values are capped to limit their influence. So these are things we need to keep in mind for data cleanup. Now that we've cleaned our data, the next step is data normalization and scaling. This is crucial because many machine learning algorithms, particularly those based on distances, like KNN, are sensitive to the scales of features. Data normalization is the process of organizing data in a database to make it easier to work with and analyze. We are spring cleaning the data. To normalize a dataset, you reorganize it to remove any unstructured or redundant data. Why is this important? It helps standardize data. Data normalization creates a standardized format for data across an entire system. This includes creating tables and establishing relationships between them. It also reduces redundancy. Normalization eliminates redundant data, which can waste disk space and make maintenance difficult. It improves accuracy. Normalization improves data accuracy by removing data irregularities. Finally, it makes data more manageable. Normalized data is easier to manage and allows for faster and simpler searches and analysis. First, normalization by min and max scaling. Min and max scaling rescales the values of a feature to a range between 0 and 1. This can be particularly useful when features are measured on different scales or units. Here is this formula. Don't memorize it, just understand we do it. This is the beginner course, right? After normalization, the minimum value will be 0 and the maximum will be 1, ensuring that no single feature dominates the calculations. Next, we also have standardization with the z-score normalization. In this method, we transform the data to have a mean of 0 and a standard deviation of 1. This is especially useful for algorithms that assume the data follows a Gaussian distribution. Here is that formula. With the /mu representing the mean and /sigma, the standard deviation. Standardized data retains the underlying distribution, mitigating the influence of outliers. Again, not for memorization, but just try and wrap your head around it a little. So we have looked on the surface anyway at data cleanup and data normalization. Finally, we arrive at data encoding techniques. Data encoding is the process of converting data from one format to another, typically transforming categorical data into numerical representations so that computers and machine learning algorithms can easily process and understand it. Data encoding is basically acting as a translator between raw digital information and a human-readable format, ensuring compatibility across different systems. You see, many machine learning algorithms require input data in numerical format, so we must convert categorical data into a numeric representation. I know this all sounds crazy, but you need to start the understanding process. So one way of data encoding is one-hot encoding. That's a cool name for something, by the way. One-hot encoding. One-hot encoding transforms categorical variables into binary vectors. Each category is represented as a vector with a length equal to the number of categories. Binary vectors, right. Are your eyes rolling back in your head yet? A binary vector is a way to represent complex objects, such as text, images, or audio, as fixed-length binary values. So a binary vector can represent the presence of keywords in text content. In this case, each dimension of the vector corresponds to a word in the vocabulary. An additional one indicates the presence of the word in the text. Before your eyes glaze over, let me give you a simple example. Say we have a categorical feature, color, with categories red, green, blue. Here is how we can encode it. So there are three categories. The length of the vector is 3, so red equals 1, 0, 0, and green equals 0, 1, 0, and blue equals 0, 0, 1. When our ML sees color, it no longer has to say, dude, what is this RED? It knows 1, 0, 0, 0. This method avoids the potential issue of ordering in categorical data, but can lead to high dimensionality when dealing with a large number of categories. That is one-hot encoding. How about label encoding? Label encoding assigns each unique category in a feature an integer label, for the same color example. While this approach is simpler and maintains dimensionality, it introduces an unintended ordinal relationship which may not exist. What is mean is the machine may see 1 is to 2 and 2 is to 3 as having meaning. Is it a rank? Are the differences the same but 1 is to 3 is different? So you may actually invite complications you did not mean to. So how do you choose between one-hot and label encoding? The choice between these techniques depends on the nature of your data and algorithms. Let's oversimplify this. First, remember the nominal and ordinal data types. Nominal is data that is categorized without an order or hierarchy, like hair colors. Ordinal data has a hierarchy, like is a survey. You label things terrible, bad, no opinion, good and super. There is an order, so now that we did that reminding, use one hot encoding for non-ordinal categories to prevent misleading relationships. So the hair colors use one hot. Use label encoding primarily for ordinal data where categories follow a meaningful order. So with the survey terrible equals 1, bad equals 2, no opinion equals 3, you get the idea. To wrap up, we've covered the fundamental aspects of data pre-processing, including data cleaning for addressing missing values and outliers, data normalization and scaling to standardize our features, and data encoding techniques to convert categorical data into numerical format. Remember, successful pre-processing is a crucial step that helps in building robust machine learning models. By investing time into these processes, you ensure that your models can generalize well to unseen data, increasing their effectiveness. Thank you for your attention. And I look forward to our next session. I know this is getting a little tougher, but remember what Malcolm X said. Education is the passport to the future. For tomorrow belongs to those who prepare for it today. Cheers and have a blessed day. Please like and subscribe for the sake of Tech Skill Hub and all AI avatars who need the work. This is Ethan signing off.